Jai Hind everyone. This is Dr. Naresh Kumar from Akgec Engineering College, Ghaziabad. Welcome to the class of Communication Engineering. In this lecture, basically we will continue the frequency modulation from the previous lecture, and we will also discuss the phase modulation, which are basically covered under the main heading, that is angle modulation. So in this mainly we will continue the frequency modulation, and we will also compare the concept of frequency modulation along with the phase modulation. We will also cover some numericals for this topic along with the derivation and waveform for the phase modulation. So basically we are talking about angle modulation in this lecture. We have earlier studied that the modulation is the process of conveying information using the communication system in which the characteristics of the carrier signal are changed according to the message signal. So that is, in the modulation we vary the characteristics of the carrier signal. These characteristics may be, for example, the amplitude, may be the frequency, and may be the phase of the carrier. So these are the three characteristics that can be mainly varied for the carrier signal. In the angle modulation, basically these two type of modulations are covered under the heading angle modulation. Okay. Basically modulation is required to achieve the long distance communication. Modulation is also required for achieving the narrow banding concept. Modulation is also required for achieving the multiplexing. Modulation is also required for ensuring the practicality of the antenna or size or height or dimensions of the antenna. So these are the four main reasons why we use the modulation process in the case of communication system. So as we have studied, the modulation is varying of the characteristics of the carrier signal. So let's say we can say that if we have a carrier signal, let's say Vc cos of omega ct plus phi. Okay. So these two terms, when we vary the frequency, because omega is 2 pi fc, so when we vary the frequency, this term is changed in the frequency modulation, and when we vary the phase, okay, then let's say denoted as theta. So this theta is varied along the carrier according to the message signal. So basically when we vary the frequency or phase of the signal, we are changing this angle. That's why the modulation technique is known as the angle modulation. So basically in the angle modulation, we vary the frequency or phase of the carrier signal in accordance with the message signal. So either we can vary this f or we can vary this phase of the carrier signal according to message signal. That's why this angle modulation can be divided into two types: frequency modulation, where the frequency of the carrier is changed according to the message signal, and phase modulation, where the phase angle of the carrier signal is changed according to the message signal. So the concept that I have discussed related to frequency modulation and phase modulation can be summarized here. For example, phase modulation is changing the phase of the carrier is changed according to message signal. So let's say we have a carrier signal EC cos of omega ct plus kp into xt. Okay, that is, this phase angle is changed according to the message signal xt, where this kp is the phase sensitivity value. It is known as the phase sensitivity, that is varying of the phase rate along with the amplitude. So in the similar way, in the frequency modulation, we vary the frequency of the carrier signal according to message signal. That is, the instantaneous value of frequency can be obtained by changing the carrier frequency accordance with the message signal. So, we have taken Kp for the phase sensitivity. Now, for the frequency sensitivity, we will have Kf into message signal xt. Okay, and this Kf is again the phase sensitivity. So, the frequency sensitivity in the unit hertz per volt. So, in the angle modulation, basically we vary the angle component of the carrier signal according to message. That angle component may be the frequency or the phase of the carrier signal. Now, next is basically the types of FM. In the previous lecture, we have discussed the concept of frequency modulation, and again I have repeated. The FM can be divided into two types. One is narrowband FM. Another type of FM is wideband FM. So, basically these are the wideband and narrowband FM are basically the types of FM signals. So, as compared the narrowband and wideband. So, based upon some parameters, when the values are less, we will say that it is narrowband FM. For example, in the case of narrowband FM, all the values corresponding to modulation index, maximum deviation, frequency deviation, range of modulating frequency, maximum modulation index, bandwidth, etc. All these values will be in the lower side or lower range for the case of narrowband FM, and all these values will be on the higher side in the case of wideband FM. For example, the modulation index in the narrowband FM is approximately 1, nearby 1, but in the case of wideband FM, it is generally greater than 1 or generally at higher side. The maximum deviation delta F max allowed is 75 kilohertz in the case of FM, wideband FM, whereas it is very low, that is 5 kilohertz in the case of narrowband FM. Then we have range of modulating frequency is up to 15 kilohertz in the case of wideband FM, whereas in the case of narrowband FM it is maximum up to 3 kilohertz. As discussed, modulation index can be generally on higher side in the case of wideband FM, and it is approximately or nearby 1 plus, slightly plus or more, and bandwidth is comparatively sorry, the bandwidth in the case of wideband FM is approximately 15 times more as compared to the narrowband FM. In the case of narrowband FM, the bandwidth is approximately same as that of amplitude modulation. The main applications are, as clear from the bandwidth of wideband FM is more, so wideband FM is comparatively more suitable for the case of entertainment applications or where the data rate requirements are high or quality is high. So, this can be used for the case of like music transmission or entertainment purpose, whereas this narrowband FM can be generally used for mobile communication, police wireless, ambulance system, etc. And in both the cases, the pre-emphasis and de-emphasis can be used for increasing the magnitude levels at the higher frequencies to increase the threshold SNR value. So, next is spectrum of wideband FM. Basically, the equation for FM is generally very complex, and mathematically it can be represented through Bessel functions. Bessel functions are used for representing the equations for the FM wave. So, in the wideband FM, this is the equation corresponding to the wideband FM modulated signal, where we can see that we have a carrier signal, then we have a number of sidebands. Okay, so in the wideband FM, we have a number of sidebands, Ideally, the number of sidebands in the wideband FM are infinite, but practically the number of sidebands are very high. So, the equation for the wideband FM can be represented through Bessel functions. Now, the spectrum, this is the spectrum for wideband FM. If we plot the terms corresponding to the Bessel function or FM equation corresponding as shown in the previous slide, we have the number of sidebands are ideally infinite, and we can see that from this central frequency, as we increase the frequency, the magnitude of the sideband components keep on decreasing. Okay, from the FM spectrum it is clear that the magnitude of the FM sideband components keep on decreasing, or we can see that only the starting few sidebands are significant sidebands. Only few sidebands are significant, whereas the remaining sidebands can be treated as insignificant and can be ignored. That is, for calculating the bandwidth of the wideband FM, we consider only the selected number of sidebands which are significant enough. Okay, so here we can see that the spectrum of FM signal. Now, how we can calculate the bandwidth? Bandwidth of FM. Basically, the bandwidth depends upon the number of sidebands. In the case of ideal scenario, the number of sidebands are infinite. So, in the ideal case, the bandwidth of the frequency modulation will be infinite, but practically the number of sidebands which are considered are those only which are significant in number. So, for calculating the bandwidth in the practical region, we consider only the significant sidebands. So, the formula for bandwidth of FM will be given as twice FM into number of significant sidebands. Okay. So, if we consider one sideband, then the bandwidth will be equal to AM, that is 2 FM, and depending upon the significant number of sidebands, the bandwidth can be calculated. For practical cases, the approximate bandwidth for the case of FM, which case is wideband FM, can also be given by a rule known as the Carson's rule. Okay, so basically Carson rule define the bandwidth of the FM in the approximate value range for the practical cases. So, the bandwidth in the Carson rule is given by bandwidth equal to twice of delta F, that is deviation, plus maximum frequency component. This F is FM max. Okay. So, the approximate value of bandwidth for the case of wideband FM can also be calculated using this Carson rule. Okay. So, let us see some numericals. So, this is one numerical based upon the FM frequency modulation. What we are given? We are given an angle modulated voltage, this one. Okay. Calculate the carrier and modulating frequencies. Okay. If we compare this given equation with the standard FM equation, we can easily calculate the this 10 is basically EC, or we can say that the magnitude of carrier is given as 10. And if we compare, it is 2 pi FC. 2 pi FC is, if we compare, it is 10 raised to power 8. So we can calculate as 2 pi FC equal to 10 raised to power 8 hertz. Okay, because this is omega is 2 pi f. So if we compare with the standard equation, this f is basically the carrier frequency. So carrier frequency can be calculated as fc equal to 10 raised to 8 divided by 2 pi. So this comes out to be as 15.91 megahertz. In the similar way, if we compare again with the standard equation, this one is there. So given equation is compared with the standard angle modulated FM equation. So we can have 2 pi FM equal to 10 raised to power 4, that is FM equal to 10 raised to power 4 by 2 pi. So in this way we can calculate the modulating frequency also. FM can be calculated as 1591.5 hertz. And if we compare the standard equation, we have modulation index equal to 3. So we have modulation index equal to 3. And we know that modulation index MF equal to delta F by FM. Okay. So in this way we can calculate the deviation delta F equal to FM into MF. Both the values are given. MF equal to 3 and FM equal to 1591.5. So again we can calculate the deviation. It is 4.774 kilohertz, that is nearly 5 kilohertz. So again in the end what we have to calculate is power dissipated across the 100 ohm resistance. R is given as 100 ohm. Okay. So we know that power equal to V equal to average power equal to P equal to V square by 2 into R. Okay. So this V magnitude is as 10. So it is 100 divided by 2 into R is again 100, it is given. So putting this value, we can have 0.5 watt. Okay. So the power is constant for the case of FM, that is 0.5 watts. Okay. We can also calculate the bandwidth for this using Carson rule. If we have to calculate the bandwidth also for this numerical, we can have bandwidth 2 into delta F plus FM max. So we can also calculate as 2 into delta F. Delta F is given as 4.774 plus FM. FM is this one 1591.5. So we can also easily calculate the bandwidth for this FM system. Let's see another numerical where we have to compare the bandwidth using Carson's rule. We are comparing the bandwidth using the Carson's rule for the case of narrowband FM versus wideband FM. So as per the given values, we are given a baseband signal with frequency range 1300 Hz to 3 kHz. So baseband signal is given with range is given. So FM max is 3 kHz. So we will apply the Carson rule. As per Carson's rule, the bandwidth is 2 into delta F plus F max, where this F max is 3 kHz. Now, firstly, the case is there narrowband FM. For the case of narrowband FM, the maximum deviation is 5 kHz. So for the case of narrowband FM, the maximum deviation is 5 kHz and the F max is 3 kHz. So putting the value, we can get the bandwidth for the case of narrowband FM is nearly 16 kHz. Now for the case of wideband FM, the delta F max is 75 kHz. So putting in the Carson's rule, delta F max as 75 kHz and this F max is already 3 kHz. So again putting the value using the Carson's formula, we can calculate the bandwidth for wideband FM as 156 kHz. From this we can see that there is a huge difference between the bandwidth of narrowband FM when compared with the wideband FM. So in this case we can see that approximately the bandwidth is 10 times more in the case of wideband FM as compared to narrowband FM. So let's have a derivation for the phase modulation. Okay, so phase modulation, as we have already discussed, we have a carrier where the phase of the carrier is changed according to the message signal, where this K is the phase sensitivity component and combinedly this Km into Vm can be put it as MP, that is modulation index for the case of phase modulation. Similar to the previous numerical, we can write the standard equation for the phase modulation from the given values. This omega c can be calculated using this Fc, where this Vm is 5 volt, phase deviation is 25, so it is 25 here, and then we have this is omega c, that is 2 pi Fc, and this is omega m, that is 2 pi Fm. So we are already given with Fm, we are already given with Fc, also will be given as, so Fc is also given, so we can write the standard equation for the phase modulation. Again here we are given the standard equation. If we compare, we can calculate the Fc by dividing 2 pi, we can calculate the Fm by dividing 2 pi, and this is the modulation index for the phase modulation. This is the waveform for the standard phase modulation, where we have a modulating signal and a carrier signal, and as per definition, the phase of the carrier signal is changed according to the message signal or modulating signal. So here the amplitude is maximum and it is now going down decreasing. So at this point there will be phase shift. So again there we have a minimum point, at this also point we have a phase shift. this is the comparison slide for basic differences between the frequency modulation and the phase modulation. However, the main difference is the change in the angle of the carrier signal. If we change the frequency of the angle part, that is frequency modulation according to message, and if we change the phase of the angle, that is phase modulation. So the main difference can be summarized, we can be seen here. So that's all for this lecture. Thank you everyone. This is the reference and